So let's pull back the curtain on artificial intelligence. Forget for a second all the talk about massive, complicated algorithms or futuristic neural networks. Because today, we're talking about the one deceptively simple idea that is the engine running underneath almost all of it.
So what is it? What is this foundational concept that allows a machine to learn from data? I mean, whether it's figuring out what's a spam email or writing an entire essay, what's the core principle at play?
And there it is. That's the big secret. Choose the model that performs best on the data you have observed. I know, it sounds almost obvious, right? Like, of course you do that. But trust me, this single sentence is the heart of a powerful principle that has shaped the entire field of AI. Okay, let's dive into this. This principle has a formal name, Empirical Risk Minimization, or ERM for short. Now, it's really important to get this straight. ERM isn't an algorithm itself. It's more of a guide, a philosophy, really, for how you should even approach the problem of learning from examples. Let's just break that name down. Empirical just means based on stuff you've actually seen, your data. Risk, that's just a formal word for error or mistakes. And minimization, well, that just means making that error as small as you possibly can. So ERM is just telling us, look at your data and pick the model that screws up the least. That's it. It's the compass for machine learning. But, this immediately brings up a big question. How do we define what best even means in a mathematical way? And how do you measure when a model is wrong? To do that, we have to get a little more specific about this idea of risk. Let's make this real with a classic example. Imagine you're building a spam filter. You don't have some universal law of spam. What you do have are thousands of emails that have already been labeled. Your job is to look at all those examples and somehow figure out a rule that's going to work on new emails it has never, ever seen before. So how do you find the one best rule out of all the infinite possibilities? Okay, this is where things get really interesting. Ideally, what we'd love to know is a model's true risk. That's how well it would do on every single email that has ever been written or ever will be written. But that's impossible, right? You can't see the future. So we do the next best thing. We take a sample, our data set, and we measure the empirical risk just on that sample. It's our best guess at the real thing. And to actually calculate that error, we need one more tool, a loss function. Think of this as our definition of wrong. It's a little function that dishes out a penalty score for every single mistake the model makes. So for predicting house prices, being off by a few dollars might be a tiny penalty. But for medical diagnosis, being confidently wrong could get a massive penalty. The loss function makes the goal totally concrete. So now we've got all the pieces, right? We have our data, this idea of risk, and a loss function to measure it. Now we can finally see how this simple idea becomes the powerhouse engine inside all those famous AI algorithms you hear about. It doesn't matter if it's something as basic as linear regression, just trying to fit a line to some points, or a massive neural network learning to write poetry. The core process is exactly the same. They all have a loss function defining their goal, and they all use some method, like gradient descent, to just tweak their internal settings over and over and over until they've minimized their empirical risk. It's ERM in action, absolutely everywhere. But there's a twist. There's always a twist, isn't there? This simple, powerful principle has a dark side, and following it too perfectly can lead to, well, spectacular failure. Just think about it for a second. What happens if a model gets so good at minimizing mistakes on the data it has seen that it learns it perfectly? This is what we call overfitting, and it is the central vulnerability of ERM. The model doesn't just learn the underlying pattern, it actually starts to memorize every single detail of the training data, including all the random noise and weird quirks. Its empirical risk might be a perfect 0. But the moment you show it some new data, it just completely falls apart because it never learned the general rule. And this slide just shows that difference perfectly. On the left, you've got a model that gets the general trend. That's good. On the right, you've got an overfit model that is desperately trying to hit every single data point, even the random outliers. It's like a student who memorizes the answers to a practice test but doesn't actually understand the subject. They'll ace that practice test, sure, but they are going to fail the final exam.
So the crucial question becomes, how do we get all the benefits of ERM without falling into this trap of overfitting? Well, we have to give our learning process some guardrails. The first guardrail is about limiting the model's options. We call this the hypothesis space, which is just a fancy way of saying the set of possible solutions the model can even choose from. So instead of letting the model draw any crazy line it wants to fit the data, we might say, nope, you can only use straight lines. By restricting the model's creativity, we make it much harder for it to get lost in the noise and overfit. The second guardrail is incredibly powerful, and it's called regularization. Here, we actually change the rules of the game. We tell the model, your goal isn't just to be accurate. You also get penalized for being too complex. So now, the model has to find a balance. It's like telling a student, I want you to get the right answer, but I'm going to deduct points if your explanation is a long, convoluted mess. This forces the model to find simpler, more elegant solutions that are way more likely to be correct in the long run. Okay, let's zoom out. We've gone through the mechanics and the pitfalls, but what does ERM really tell us about the nature of learning itself? At its very heart, ERM is a philosophy. It formalizes an intuition that all of us share. The way you get better at something is to look at your past mistakes and try not to make them again. It's how we learn as humans, and ERM is just the translation of that simple idea into the language of mathematics for machines. And understanding this philosophy has huge practical benefits. It clarifies why we choose certain loss functions, why we use things like regularization, and how to diagnose problems like overfitting just by looking at a training graph. It's the unifying theory that connects all of our day-to-day practices. So we'll leave you with this. Empirical risk minimization is the powerful, quiet engine that has driven machine learning to where it is today. But its core principle is all about learning from the past. So the really big question for the future is, if our most powerful learning tool is based on minimizing past mistakes, how do we build AI that can go beyond that, to imagine and create a future that isn't just a reflection of the data it's already seen?